Welcome back to the clustering module. In the previous video, we saw the concepts of intra-cluster distance and inter-cluster distance. And we associated each of them with the two properties of the clusters that we covered earlier. So we can say that all the points in a cluster should be closer to the centroid of that cluster, and the centroid of different clusters should be as far as possible. There is an algorithm which tries to minimize the distance of the points in a cluster with their centroid. This algorithm is k-means. Let me first give you a brief overview of what k-means is, and we later deep dive into it. K-means is a centroid based algorithm, or we can call it a distance based algorithm, where we calculate the distances to assign a point to a cluster. I'll be talking more about these distances and how to assign a point to a cluster later in this video. In k-means, each cluster is associated with a centroid. So each cluster, you can say, is defined by its centroid. The main objective of the k-means algorithm is to minimize the sum of distances between the points and their respective cluster centroid. I'll again recall the first property of a cluster, that the points in a cluster should be similar to each other. This is exactly what k-means tries to achieve. If the distance between the points in a cluster and its centroid is minimized, there is a high chance that those points will be similar to each other. And that's exactly what we'll do in k-means. Let's take an example to understand how k-means actually works. Consider that we have these 8 points and we want to apply k-means to cluster these points. The first step is to pick the number of clusters k. And once we have the number of clusters, we can randomly select the centroid for each cluster. Let's say we want to have 2 clusters, so k will be equal to 2 here. We then randomly select the centroid. Here the red and the green circles represent the centroid for these clusters. Once we've initialized the centroids, we can assign each point to the closest cluster centroid. So the points which were closer to the red point have been assigned to the red cluster, whereas the points which were closer to the green one have been assigned to the green cluster. Straightforward, right? Now, once we've assigned all of the points to either of the clusters, we need to compute the centroids of these newly formed clusters. Here, red and green cross are the new centroids. We then repeat steps 3 and 4. So we'll calculate the centroid of the newly formed clusters, assign points to the nearest cluster centroid, again calculate the centroid of the cluster, and repeat these steps. This is how k-means works. Here the step of computing the centroid and assigning all the points to the cluster is a single iteration. You must be wondering, when in the world do we stop this process? So let's look at some of the stopping criteria. We can stop the algorithm if the centroids of these newly formed clusters do not change. Even after multiple iterations, if we're getting the same centroids for all the clusters, we can say that the algorithm is not really learning any new patterns, and it's a clear sign that we should stop the training process. The second criteria is if the points belong to the same clusters, even after training the algorithm for multiple iterations. We can stop the training process again here. And finally, we can stop if the maximum number of iterations have been reached. Suppose if we set the number of iterations as 100, then the process will of course repeat for 100 iterations, and after that the training will be stopped automatically. These 3 are the stopping criterion, which honestly will help us decide when to stop the training process. I've been telling you from the beginning that k-means measures the distance between the points and the centroid to decide which cluster these points belong to. So the next question here is, what exactly is this distance? And how is it measuring the similarity between the points? In k-means, we generally use the Euclidean distance to measure the difference between the points and the clusters. How can we say that 2 points are similar to each other? Well, 2 points will only be similar to each other if their features are similar. If we plot these points, then they will be closer to each other. Hence, we can use Euclidean distance, and if the distance between these 2 points is less, it means these points are very similar to each other. On the other hand, if the Euclidean distance is more, then of course it's the other way. It means that the 2 points are not similar. We've already discussed about Euclidean distance in the KNN module earlier. And just to give you a brief overview of it, let's look at its formula and how to calculate the Euclidean distance between 2 points. It'll be a nice refresher. Here's the formula for Euclidean distance. N is the number of variables and P and Q here are the data points. Very simple, right? Now, since k-means is a distance-based algorithm, the scale of the points can affect the performance of the algorithm. Consider your data has an age variable, which tells us about the age of a person in years, and an income variable, which tells the monthly income of the person in Indian rupees. Let's say this is a sample of the data. If we look at the age variable, it ranges from 25 to 40, whereas the income variable ranges from 50,000 right up to 1,10,000. Let's try to find the Euclidean distance between the first 2 points. This is how we can do it. And it'll be somewhere approximate to 20,000.000625. You can see the high magnitude of income has affected the distance between the 2 points. This will impact the performance of our k-means model, as it will give a higher weightage to variables which have higher magnitude, as you can see with income in our example. We don't want our algorithm to be affected by the magnitude of these variables. It'll throw our model into a tizzy. So what can be the solution? How can we find a workaround for this? We can scale all the variables to the same scale. One of the techniques to scale them is normalization. In normalization, we subtract the means of the variables and divide by their standard deviation. I won't go into the details of how normalization works. If you want to learn more about it, feel free to refer to the link which we've provided below this video. Let's just spend a few moments understanding how normalization helps to bring all the variables to the same scale, and which of course improves the k-means algorithm. In normalization, we calculate the mean and standard deviation of the variable. And for each observation, we subtract the mean and then divide by the standard deviation of that variable. If we normalize both these features, age and income, the result will be what you can see on this slide. Now again, let's calculate the Euclidean distance between these 2 points. Using the same formula, we get a very respectable number, 1.1438. This distance is not only dependent on the income variable, it's now giving similar weightage to both age and income, and that's exactly what we wanted. So it is always advisable to bring all the features to the same scale for applying k-means or any other distance-based algorithm. In the next video, we'll implement k-means from scratch, which will help you to understand how this algorithm works in a better way, plus how it works in Python. Thank you.